All right, so there's a lot for me to talk about, or at least I have a lot planned for today. So I've written out sort of the agenda. I'm going to start by talking about the norm, or the length or the magnitude of a vector. I'm going to the dot product, angle between two vectors. After that, I'm going to sort of quickly recall the notion of linear combinations and span that we talked about last week, because I kind of want to tie that into linear independence. And then at the very end, I'll try to talk a little bit about matrices and matrix vector multiplication. So as I'm going along, if you guys have questions, again, and I can try to address them. All right, so let's start talking about the norm of a vector. All right, so the norm of a vector is just the same as its length. If we have a vector that's in R2, for instance, all right, so let's say here is a vector v. If you want to compute the length of this vector, let's say it has components x and y. The norm or the length, which we denote with sort of a double bar absolute value notation, the norm of v would be equal to the square root of x squared plus y squared, and that's coming from the Pythagorean theorem. So we know that x squared plus y squared would be the length of v squared, and then I just square root it to get the length of v. In R3, it works very similarly. So I'm just going to draw a picture for this as well. It's nice to see. Here's our x, y, z axes in R3. And then I'm going to try and draw a vector right now. To draw a good picture in R3, make sure that your lines are parallel to the axes. All right, so let's imagine we have this vector from the origin out to this point right here. So this vector v has components x, y, z. And if I want to get the length of this vector or the norm of this vector, what I can do is use this right triangle that I have in the picture. So we know the height of this triangle would be given by z. And then to get the length of the base of this right triangle, think of it as a vector in the xy plane with components x and y. So the length of the base would be square root x squared plus y squared, as we talked about just now in R2. So then if you use the Pythagorean theorem on this right triangle, you would get that this squared plus this squared gives you the norm or the length of v squared. And from that, you get that the length or the norm of v will be given by that formula. Okay, so it's a straightforward generalization of what you see in R2. You see that's still a consequence of the Pythagorean theorem. And then just real quickly, even though I can't really draw the picture for higher dimensions, but in general, if you have a vector v with n components, v1 through vn and rn, you can compute its norm as the square root of v1 squared plus v2 squared and so forth, all the way down to vn squared. All right. And let's just do a quick example. So let's say I have a vector v in R4. So if you wanted to compute the length of this vector, even though you can't visualize it because it's in 4 dimensions, we can still apply the formula for the norm. So it would be 2 squared plus -1 squared plus 3 squared and plus 1 squared. And adding that up will give us the square root of 15 altogether. Okay. All right, so then again, if you guys have any questions, just post them in the chat. All right, one property that I want to mention about the norm . Okay, so if we want the norm of a scalar multiple of some vector, it turns out that this will be equal to the absolute value of c, and then times the norm of the vector v. Okay. All right, so this property should be very familiar to you guys. What this is when I scale a vector v by some scalar, the length is going to be the length of v, also scaled by a factor of c. If c is negative, you know that it reverses direction, but the length still gets scaled by the absolute value of c. So that's what this property is saying. Now, if I want to, going back to this example here, we saw that this vector v has a length equal to the square root of 15. If we want a vector in the same direction as v, but with a length equal to 1, what should I do in order to get this vector? Anyone know? Yeah, okay. Yep. So we just need to scale the length down to 1. And to do that, we would just divide the vector v by its own norm, its own length. And so we would get 1 over root 15 times 2, -1, 3, and 1. All right. So this process of taking a vector and dividing it by its length, this process is important enough as to where we have a name for it. It's called normalization, as someone posted in the chat earlier. So when we say to normalize a vector, What we mean by that is to divide that vector by its length in order to get a unit length vector, which is in the same direction. So in some applications, it is necessary to be using vectors of unit length. And so it's important to know how to normalize a vector in order to get a unit vector. So as an example, towards the very end of the semester, you guys are going to talk about something called the spectral decomposition, and after that, the singular value decomposition. And both of those would require that you use unit length vectors at a certain part in the process. So therefore, it's important to know this process of normalization. All right, so that's all I want to say about the norm and the length at the moment. So I'm going to go on and talk about the dot product next. So first, just a definition. Let's say we have two vectors u and v. I'll assume these are vectors in Rn so that they have n components. Then their dot product, which we usually just denote as u dot v. The formula for the product is u1 times v1 plus u2 times v2, and so forth, all the way down at the end plus un times vn. So we're just multiplying the components together and then adding everything up. So let's just illustrate with a very quick example. Let's say u is a vector 2, -1, 1, and v is the vector 1, 3, 0. So then u dot v is going to be 2 times 1 plus -1 times 3 and plus 1 times 0. And so that gives us 2 minus 3 for a final answer of -1. So the formula is pretty simple, but you might sort of wonder, like, what's the point of doing this computation? What does this number actually represent, right? So the reason why we care about the dot product and talk about it is because this number that we get when we compute the dot product contains a lot of geometric information about our vectors. All right, so let me see what that question may have been. Yeah, so the dot product of two vectors is a scalar. The cross product, which I'm not going to talk about in my review, but the cross product of two vectors results in a vector. And if you study enough mathematics, you learn that there are many other ways that you can multiply two vectors, but we won't go into any of that. All right. So the first thing I'll note about dot products real quickly is what happens when we dot productor in itself. So if I do v dot product with v, if you think about the formula, it would be v1 squared plus v2 squared to vn squared. And if you think about it, this is actually the same as the norm of the vector v, except it's not being square rooted. So it's really the norm squared because it's missing the square root. All right. So this is a very useful formula, which I'll try to illustrate with some examples during this review. But this is one way in which the dot product contains some geometric information. You can recover the length of a vector from the dot product using this formula. And then before I go on to some more of the geometric properties of the dot product, I need to go over some of the algebraic properties of it first. So that's what I'm going to do right now. All right. So one thing that's good to note about the dot product is that it is symmetric, meaning that u dot v is the same as v dot u. And then in particular, what I want to note is that a dot product can be distributed, or it is distributive, if you will. So if you have u dot v plus w, you can distribute the dot product, and this will leave you with u dot v plus u dot w. Of course, it works the other way. So if you have u plus b dot w, you can also distribute this. And then I'll note one other property, which is that when scalar multiplication is involved, so let's say I'm doing u dot cb, the scalar, you can pull it out to the front and multiply it with the dot product. And again, if c was multiplying the first part of the dot product, you can also factor it out. All right. So then let's try to do an example problem involving some of these properties. This third property, some people refer to it as the homogeneity property. I'm not sure if that's necessarily a standard terminology, but I've seen that used before. The word homogeneous in mathematics tends to mean a lot of different things though, so I don't necessarily like the use of it, so to be quite honest. But yeah, if you want to give it a name, I would name it. All right, so let's look at an example. All right. So let's suppose we have two vectors, and we know what the dot product is equal to. Let's say the dot product was equal to -2. And perhaps we also know the lengths of u. So let's say the length of u was 3. And let's say the length of v was 1. So v was a unit vector. Using this information, we want to find the norm or the length of the vector 2u minus v. All right, so we're not given the components of u or v or anything. All we have is the 3 pieces of information given. Okay. So in order to work through this problem, what I'm going to do is I'm going to focus on computing the length of 2u minus v squared. And to do that, I'm going to use this property that we went over just a moment ago, how the norm squared is the same as the vector dot product with itself. So I can see the norm squared here is going to be 2u minus v dot product with itself. All right. So as I go through this computation, you guys let me know if you get lost, and I will backtrack and try to explain. So after setting it up as a dot product like this, the fact that dot product is distributive means that in this expression, I can FOIL it out. So I can write it as 2u dot product with 2u. And if I pull out the 2 2's, it'll be 4 u dot u. And then I'm going to get minus 2 u dot v. Next, we'll get minus, and pull out the 2, so minus 2 v dot u. And then we're going to get at the end plus v dot v. All right, so I basically just FOILed it out. All right, next, u dot product with u. We know that's just the norm of u squared. So that's just using this property once again. We know that u dot v is the same as v dot u. So I can combine these together to get minus 4 u dot v. And then at the end, we've got plus, this would be the norm of v squared. And what we can do is plug in the norm of v was 3. So this would be 4 times 3 squared, which is 9. Next, the dot product is given to be negative 2. And finally, the length of v was given to be 1. So this is 1 squared, which is just 1. And if we just finish adding this up, it'll be 36 plus 8 is 44, plus 1 is 45. So again, that was the length of 2u minus v squared. Then altogether, the length of 2u minus v would be the square root of 45. All right, any questions about that example? All right. Let's continue. Okay. So now I want to talk about the angle between two vectors. So I'll start by drawing a picture. Let's say this is U, and let's say this is V. All right, so in this picture, there are two angles that I could associate between the vectors U and V. I have this smaller angle, and then there's also this larger angle as well. So to be completely unambiguous, when we talk about the angle between two vectors, we're always referring to the smaller of the angle, or the smaller of the two angles between them. So in particular, the angle between two vectors will always be an angle between 0 and pi radians, or 180 degrees. And there's a connection between the angle between two vectors and their dot product. And to see what that connection is, here I've drawn a picture of the vectors u, v, and u minus v, which connects from v to u. And here's the angle between u and v, theta. I'm going to use the law of cosines on this picture. So if you don't remember the law of cosines, don't worry too much about it. But the law of cosines tells us that in this picture, the length of u minus v squared is equal to the length of u squared plus the length of v squared minus 2 times the length of u times the length of v, and then times the cosine of the angle theta. Okay. So we get this by using the law of cosines. On the other hand, we just saw an example of how we could compute the length of u minus v squared as being the dot product of u minus v with itself. And if we FOIL this out, as we just did in the example, you'll get that this is equal to u dot u, which is the length of u squared. You get minus u dot v minus v dot u, which combine to be minus 2 u dot v. And then in the end, you're going to get plus the length of v squared. So then if you compare these two expressions for the length of u minus v squared, what you find is that for these two to be equal to each other, u dot v must have been equal to this over here. So hence we can conclude that the dot product of u and v happens to be equal to the length of u times the length of v, and then times the cosine of the angle between them. All right. So then we'll do a super quick example just to illustrate the formula. let's say I have a vector u, which is 1, 2, 2. And let's say a vector v, which is maybe negative 1, 1, 0. If we wanted to find the angle between these two vectors, first thing we would do is we need to compute their dot product as well as their norms or their lengths. So if we compute the dot product of u and v, it's going to be negative 1 plus 2 plus 0. If we compute the length of u, it's going to be the square root of 1 squared plus 2 squared plus 2 squared again, for a total of square root of 9, which is 3. The length of v is going to be the square root of negative 1 squared, which becomes positive 1, plus another positive 1, for a total of square root of 2. Then, according to this formula here, the cosine of the angle between u and v is u dot v over the norm of u times the norm of v, which is going to be 1 over 3 root 2. So then if you need the angle theta, you would do the inverse cosine, or the arc cosine, same thing, of 1 over 3 root 2. All right, let me see what's going on. Yeah, so norm is the same as the length. People also call it the magnitude as well. I've also seen the word modulus used as well. So a lot of different words for the same thing. All right. Cool. So let's talk a little bit more about this formula and some things that it says about the dot product. All right. All right. So if the angle theta lies between 0 and pi over 2, so if the angle is an acute angle, so cosine is positive in the first quadrant. So when you look at this formula for the dot product, everything on the right is positive. And so hence the dot product you can conclude will be positive altogether. But if the angle theta is obtuse, so if it's larger than 90 degrees, so that would be a picture looking more like this. Cosine is going to be negative whenever the angle is in the second quadrant, as it would be here. So look at this formula, if cosine is negative, that would make the whole thing negative. So you would find the dot product will be negative in this case. So you can sort of roughly remember this as saying that if the two vectors, if they kind of point in the same direction, the dot product will be positive. Whereas here, if they kind of point more in like opposite directions, then the dot product is going to be negative instead. So therefore, the sign of the dot product, whether it's positive or negative, gives you some sense regarding the orientation of your two vectors, whether they are closer to pointing in the same direction or whether they are closer to pointing in opposite directions. So that's kind of what the sign of the dot product can tell you. For the special case where the angle is pi over 2, it's a very special case. Cosine of pi over 2 is equal to 0. So that means that when our vectors are perpendicular or orthogonal to each other, their dot product will be equal to 0. So we will say that two vectors u and v are orthogonal to each other. Orthogonal being pretty much the same as perpendicular. So two vectors are orthogonal if and only if their dot product is equal to 0. All right. Now at this point, let me also briefly mention the Kosher, Schwartz, and triangle inequalities. Okay, so Cauchy-Schwarz inequality comes from this formula that we just derived for the dot product. All right, so we know that cosine is always between -1 and 1. So if you will, the absolute value of cosine is less than or equal to 1 altogether. So combining these two together, we can say that the absolute value of u dot v will be less than or equal to the length of u times the length of the vector v. Okay. So all we basically did is drop the cosine and say that it's less than or equal to 1 in absolute value. So the dot product will be less than or equal to this altogether. This is the Cauchy-Schwarz inequality. Regarding the triangle inequality, if we look at the length of u plus v squared, and I do what we've done a couple of times already in this review and FOIL this out. So probably you guys are good with this by now. It's the length of u squared plus the length of v squared plus 2 u dot v. And if I use the Cauchy-Schwarz inequality here, I can say that this dot product will be less than or equal to the length of u times the length of v. So then we can get that the length of u plus v squared will be less than or equal to the length of u squared plus the length of v squared. And I'm just going to replace this with the length of u times the length of v. And by doing that, I get something that's bigger than what I started with. All right. But then this altogether, you might notice it's just the length of u plus the length of v all squared. Right, so if you FOIL this out, you would get exactly what you have up here. And then square rooting both sides would give you the triangle inequality. The length of u plus v is less than or equal to the length of u plus the length of v. And so that's the triangle inequality. So I wasn't exactly planning on doing that, but I know someone asked, so I'll at least mention them. How did I get less than or equal to? Let's see here, let's go back to, okay. So what I did is I replaced the dot product of u and v with the product of their norms. And Schwartz tells me that the product of the norms is larger than the dot product. So by replacing the dot product with something larger, that means this expression overall is larger than the expression that I started with. So that's where the inequality comes from. And then from there, I rewrote this as a perfect square and square root both sides. And that's how I got the triangle inequality. Right, yeah. So these two inequalities, all right, so Kosher Schwartz is important because it gave us the triangle inequality. The triangle inequality, well, sure. So let's talk a little bit about just why we call it the triangle inequality first. I'm sure some of you already know that. But if we connect u and v head to tail, we know that there's some forms the third edge of this triangle here. So the triangle inequality is saying that the length of one edge of a triangle is less than or equal to the sum of the remaining two lengths. So this is a well-known geometric fact about triangles. And that's where the name of this inequality comes from. And this triangle inequality, it's arguably possibly one of the most important results in all of mathematics. Just in the sense of how useful it is in proving other results in mathematics. Any math major will probably tell you that the triangle inequality is the one result that they used more than any other result in all of their classes. So that's why it is extremely important. In this class, you guys aren't going to be doing much with either of these inequalities, aside from the few questions I have in this homework assignment, possibly a question on an upcoming quiz or exam over this material. But aside from that, I won't really be doing with these inequalities in this class. Now, I won't work through that homework problem that you're asking about, but I'll give some. I'll talk a little bit about it because it is a tricky question. So in the homework, you were asked to prove two inequalities using the triangle inequality. So you were asked to show that the length of u minus v is also less than or equal to the length of u plus the length of v. And then the other one, which is a little bit more tricky, was that the length of u minus the length of v is less than or equal to the length of u minus v. And maybe before I go just a little bit into this question, does anyone actually know how to prove either of these inequalities, the triangle inequality? Yeah, did anyone manage to figure out this problem? Okay. Okay, sure. So the key idea to proving these using the triangle inequality, what you want to understand is that the triangle inequality is true for any two vectors. So like the u and v written up here are not referring necessarily to the u and v in these questions. So let me rewrite the triangle inequality by using a and b instead of u and v, just to not confuse both the u and v in the question. All right, so as someone suggested in the chat, you can try to apply the triangle inequality to the case where A is the vector u in our problem, and B is the vector not v, but if you let B be the vector negative v instead, and you plug these into the triangle inequality, it would tell you that the length of A plus B is less than or equal to the length of A plus the length of B. And probably at this point, most of you see that first inequality. And I won't do the second one, it's a little bit harder. But if you do want to ask me some more questions about that one, I'll save it for after the review. All right. So stick around afterwards if you still want a little bit more help with that second part, and I'll help you some more. All right, so any other questions? All right, so I'll say just a little bit more about this formula that we've been spending some time with. Okay, so as I noted earlier, we know that cosine is always between -1 and 1. In particular, cosine will be equal to -1 at the angle of pi, and cosine will be equal to +1 at an angle of 0. So when you're thinking about the maximum and minimum values that the dot product can take on, okay, so this expression will be maximal when over cosine is as large as possible, meaning when cosine theta is equal to 1, then you would get that u dot v is equal to the length of u times the length of v. Whoops. And so this happens when the angle between u and v is equal to 0, meaning, as in my picture here, that they would point in the same direction. So the angle between them would be 0 in this case. And the sort of other extreme, if the vectors u and v point in opposite directions, so the angle between them would be 180 degrees or pi radians, then cosine would be -1, and you would find that u dot v is negative the norm of u times the norm of v. So this happens when the angle between them is pi. And then this will give you the largest and smallest possible value of u dot v that depended on the angle between them. And finally, just want to say, just do one more example perhaps. If we wanted to find the max and min values of, let's say, u plus v, as you guys have seen so often in this review, it's often much easier to look at the square of the norm of a vector, precisely because you can translate it into a dot product. So I'm going to do this. I promise this will be my last time, at least the last time that I have planned for this review. So I expand it into the dot product and FOIL it out. And when you FOIL it, you should end up with this. So that would be the length of u plus v squared. So let me maybe just copy that down here now. So then thinking about how large can this expression be? Well, we know that u dot v, the largest the dot product could be, is the length of u times the length of v. So if I replace u dot v with the norm of u times the norm of v, this should give me the largest possible value, just because that's the largest that the dot product could be. And then similarly, the smallest that the dot product could be is the negative of the norm of u times the norm of v. So by replacing the dot product with its smallest possible value, that gives me the smallest possible value. For the length of u plus v squared. And so again, this maximum would occur when the angle between u and v was 0. And this minimum would occur when the angle between them was pi. All right. Any questions about any of that? All right. So I want to talk about linear independence. And before I get to linear independence, I wanted to just do just like one small example, just sort of recalling some of what we got last time. So I want to just recall the notion of a linear combination in particular. So remember that a linear combination of some vectors v1, v2 to let's say vk, it was anything or any vector of the form c1 v1 plus c2 v2 plus down to ck vk, where the c1, c2, and so forth, all the c's are scalars. All right, so basically a linear combination of some vectors, it's sort of like just a combination of scalar multiplication and addition of those vectors. It's basically all a linear combination is. We talked about how when we have two vectors, u and v, that look like this, we talked about how the span of u and v, which we defined to be the set of all linear combinations of u and v. We talked about how the span of u and v would be a plane, specifically the plane that contains the two vectors u and v. All right, so look at just a very quick example. Let's say I have two vectors u and v. And then let's say I have a third vector w. which I'm going to say is equal to 1, 3, and oh, sure, let's do 1, 3, 2. So let's say if I have this vector W and I want to ask, is W a linear combination of the vectors U and V? And I could also ask, is W in the span of U and V? I could also ask if W in the plane containing U and V. Okay, so these three questions are all the same question, right? Because to say that W was in the span means that W was a linear combination of U and V. And because the span of U and V, you can see that U and V, they're not multiples of each other, so they're not collinear. So they would form a plane. And asking if W is in that plane would be the same as asking if W was in the span, because the span would have been the plane containing U and V. So here is just maybe showing you guys how they can ask the same question in multiple different ways. So you want to understand the connection between different things in order to answer the question however it may appear to you. All right, but to answer this question, what we would do is take the vector W and we would just try to set it equal to a linear combination of U and V. And we just want to see, can we solve for C1 and C2 that will satisfy this equation? And so if we wanted to try and solve for C1 and C2, by reading off the components, you get a system of equations. Looking at the x components, you get 1 equals 1 C1 plus 0 C2. Looking at the y components, you would get 3 equals 2 C1 plus 1 C2. And finally, looking at the z components, you would get 2 equals 1 C1 plus 1 C2. And then you would want to try and solve this system of equations. If C1 is equal to 1, from the second equation, you would get that C2 has to equal 1 as well in order to add it to 3. And if C1 and C2 are both equal to 1, that just so happens to satisfy the third equation as well. So we did find a solution to the system of equations. And therefore, we see that the vector W was equal to 1 times U. So plugging in 1 for C1, plugging in 1 for C2, so plus 1 times the vector V. So because we found a solution to the system of equations, that means that W is a linear combination of U and V. And so the answer to all of these questions would be yes, all right? So I'm going to see what that was. Yeah, so now I want to talk about linear independence. So it is true that the three vectors u, v, w here would be linearly dependent. So let's talk about why that is the case. And to do that, I need to talk about what linear independence is. All right, so there's many equivalent definitions for linear independence, all of which are good to know. Because as you can see in the previous example, they can ask the same question in different ways. So you'll want to understand how to think about the same thing in different ways to be prepared for the different ways they could come up in a question. So first I want to talk about linear independence from a geometric perspective. So I want to first consider if we have two vectors u and v. Okay, so one possibility with these two vectors is that they would look like this, and they would span a plane. Another possibility is what we call linear, in which case they would only span a line. And then in a sort of extreme case, if they were both equal to 0, they would only form a point. All right, so a plane, geometrically, we can think of a plane as being a 2D, two-dimensional object, because a plane has area associated with it. A line would be a one-dimensional object, because lines have length associated with it instead. And a point would sort of be like a zero-dimensional object. It doesn't really, I guess, have any dimensions associated with it. And you guys are actually going to talk more about dimension in this class, but for now, just having this intuition, 2 dimensions corresponds to having area, 1 dimension corresponding to having length. All right, so with two vectors u and v, they will be linearly independent in the case that they form or that they span a 2-dimensional plane. If they span less than 2 dimensions, then they would be linearly dependent instead. And it's kind of similar if you have 3 vectors as well. So imagine having 3 vectors u, v, and w. So the nice case would be when your 3 vectors span 3 dimensions. So here in the picture, I tried to draw W sticking above the plane containing U and V. So they stretch out in 3 dimensions. Okay. In this case, UVW would be linearly independent. And in every other case, if they are coplanar, meaning they would only span a plane. If they were collinear, meaning they only span a line, or if they were all zero, meaning they would only span a point, then they would be linearly dependent. Okay. So what it means for a set of vectors to be linearly independent, it means that they're spanning the maximum possible of dimensions. So more precisely, let's say if you have k vectors, v1 through vk, we can say they are linearly independent if they span a k-dimensional space. Okay. So this is what linear independence means geometrically. If they span less than k dimensions, they would be linearly dependent instead. All right. So again, this is, I think, very good to know. However, it doesn't really help you in solving many questions because it's very hard to visualize. Talk about how to think of linear independence more algebraically. And this will probably be my final topic for the review since I am running out of time at this point. So going over an algebraic definition of linear independence. Okay, so there are 2 definitions, each one having its own use, and therefore good to know both of them once again. I'm just going to state what the definitions are. So we can say that V1 through Vk are linearly, I'll start with linearly dependent if one of these vectors is a linear combination of the others. Then they would be linearly independent otherwise. So meaning if none of them were a linear combination of the others. The other definition, which this one is usually easier to apply in problems. So if you had to really only remember one definition of independence, I would actually probably remember this one instead. Okay, but vectors are linearly independent if the only solution to the equation C1V1 plus down to CK Vk equals 0. So if the only solution to this equation is what people often call the trivial solution, but the trivial solution refers to the case where all of the scalars are equal to 0. This is a 0 vector. And even though I'm out of time, I'm going to try and do a very quick example because I hate to leave you guys without one. So this is going to be the very last thing I do in my review. Let's consider 3 vectors. I use really simple numbers. All right. So if I have these 3 vectors and I want to ask, are these vectors linearly independent or dependent? So it's maybe hard to visualize, so you can't quite tell geometrically. So we want to solve this problem more algebraically. And I'm going to solve this problem using this very last definition of linear independence. So what I'm going to do is I'm going to set up this equation using the vector GBW. So I'm going to set up C1 times the vector U plus C2 times my second vector V, and then plus C3 times my third vector W. And then I'm going to set it equal to the 0 vector as in the definition. And I basically want to try and solve for C1, C2, and C3. And I want to see whether the only solution is that they're all 0 or if there are other solutions as well. And so we see that this leads us to a system of equations, which I'm going to write out here. This is just, again, looking at the components of the left and the right-hand side. All right. So it leads us to the system of equations, and I'm just going to very quickly try to solve it. So perhaps solve for C1. We'll plug it into these equations now. In particular, I'm going to replace C1 with negative C2 in the last equation, which gives me minus C2 minus C3 is 0. And then next, if I try the same thing, let's say if I solve for C2 and then plug it into my last equation. So negative plug in C2 is negative C3 minus C3 is 0. This is plus C3 minus C3. So here we get something that might look unusual. We get 0 equals 0. So normally when you're solving a system of equations, you expect to get a definite answer in the end. C1 equals some number, C2 equal number, and so forth. If you haven't seen this situation before, you're going to see it a lot in this class. Anytime you get 0 equals 0 like this, when you solve a system of equations, that's an indication that there's going to be more than one solution to the system of equations. We'll talk more about that next time. But because there's more than one solution to the system of equations, that would mean that they are linearly dependent. Okay. All right. Because to be independent would mean that there was only one solution, which is the one where all the C's were equal to 0, and that's not what we got. So I'm going to end my review here. What I wanted to note is when you're checking if a vector is in the span or a linear combination of other vectors, or if you're checking if vectors are independent, both types of questions lead to the need to solve a system of equations. And because we keep seeing these systems of equations coming up, we're going to spend some time in learning how to solve systems of equations and to understand the nature of their solutions. And then once we get a better understanding of solving systems of equations, we'll revisit span and linear independence once again. But at that point, that's it for my review. So I'm going to go ahead and stop the recording.